All right, so we've talked about frequency, we've talked about the fiber diameter, we've talked about the fiber length. Those are the three factors that can influence how much force a muscle can generate. One of the other factors that we have to take into account is recruitment. So when we think about a muscle in action, a muscle that's contracting, and let's say we want to lift a small load, a light load, we can do so by having some of the fibers in that muscle contract. If we want to lift a heavier load, right, if we want to generate more force, we have the ability to recruit additional muscle fibers in that muscle, and that can allow for more cross-bridge cycling to happen, which can allow for more force to be generated, which allows for more load or a heavier load to be lifted. Okay, so the recruitment principle is this idea that more fibers contracting equals more overall muscle tension. So in order for a muscle to generate the maximum amount of force, all of the fibers in that muscle must be contracting. And so a muscle begins its contraction by having a few of those fibers contracting, and then recruitment allows for it to call on additional motor units. So each motor neuron and all the fibers that are attached to that motor neuron can be recruited, and that can allow for more force generation. So let's illustrate what recruitment looks like. So here is a motor unit X. It's one motor neuron, right? Here's our motor neuron going all the way out from spinal cord. It's going to be attaching to several fibers. And then notice motor unit X is attaching to 5 fibers, so it's a smaller unit than motor unit Y, which is attaching to 12 fibers. So it's a slightly bigger unit, motor unit Y. So let's say I'm lifting an object that requires a small amount of force. If motor unit X is contracting, that may be enough force to overcome a small load. If I want to lift a heavier object, and that requires slightly more force, I'm going to have to recruit an additional motor unit to help generate some more force. So I'm going to recruit motor unit Y, which has 7 fibers attached to that motor neuron. And so all in all, with recruiting motor unit Y, I can now generate significantly more force because I will sum the force generated by motor unit X and motor unit Y, which, as we can see here, is generating more than twice the amount of force as motor unit X generating on its own. Okay, so this is what we mean by recruitment. We can call on additional fibers specifically by calling on the motor unit to which those fibers are attached, and that will result in more force generation. Now, when we think about the recruitment, we want to think about the principle that governs recruitment. So when we look at the size of the motor unit, that's always going to be determining which units get recruited first. So more fibers contracting equal more tension. And we also want to think about the type of unit that is associated with each action. So for small actions, for delicate movements, like the movement of our fingers, the movement of the muscles of the eyes, which are really small, delicate muscles, I'm going to recruit small motor units, which have small fiber diameter, and they are attached to a small number of muscle fibers. I'm going to recruit those types of units first to do smaller, more delicate movements with smaller muscles. Now, if I want muscles for strength, this is going to require large motor units that are attached to large muscle fibers that have many fibers attached to those neurons that will also be able to generate more force because they're attached to bigger muscles. Okay, so the recruitment principle says that we're going to increase tension in a stepwise proportional fashion. Smaller activities, smaller neurons, smaller number of fibers, smaller size of fibers, more delicate movements recruited first. And then larger motor neurons, larger muscle fibers, more fibers attached, and then bigger fiber diameters, bigger muscles, and more muscles for strength will be recruited towards the end. Okay, so small first and then bigger recruited last. All right, so that's kind of just being reiterated here. Small motor units for delicate movements are recruited first, and then large motor units for strength and more powerful movements are recruited last. That applies to the diameter as well. Small fiber diameters means that there's less cross-bridge cycling, and that's going to be recruited for weaker movements like lifting a bottle, lifting a piece of paper, lifting a pen. Large fiber diameter, which will have more of those myofibrils packed in there, that's going to be required for more strength, right? More powerful contractions, and that will be recruited last. Think about lifting a piece of furniture, lifting a heavy backpack. That will recruit larger units with larger fiber diameters. Okay. Now this also applies to, again, the size of the neurons. So not only the size of the motor unit as far as how many fibers are attached, also not only the size of the fiber itself, but also the size of the neuron. So the neurons that are smaller are attached to smaller fibers. These neurons typically have smaller cell bodies and smaller axon diameters. They're really thin neurons. Those are going to be associated with smaller muscle fibers, like the muscles of your eyes, the muscles of your fingers. They will be recruited first. And then large, bulky motor units, which will have thicker neurons. Those neurons will have bigger cell bodies. Those are going to be attached to big, bulky muscles like your biceps, your triceps, your quads, your hamstrings. Those will be attached to bigger muscles in general. Okay. And so when you think about the size principle, I want you to be thinking about size in terms of all the factors. And when we say small, think about the fiber diameter. Think about the motor neuron diameter. Think about the size of the soma or cell body. Also think about the number of fibers attached to that neuron. So when we say small, think about all the factors that can be associated with that muscle fiber that are in fact small. That would include the type of action as well and the type of movement. And then large will also apply to those factors as well. The motor neuron, the size of the fiber, the number of fibers, the size of the muscle, the type of movement, all of that will be applied, that will be recruited last, okay? So the size principle means that small units are recruited first, large units are recruited last, and that applies to all of the factors that we described. And so in the illustration here on the right, here is that small motor unit X. Here's a slightly larger motor unit Y, and then here's an even larger motor unit Z. And so we recruit motor unit X first, then motor unit Y to generate more force, and then motor unit Z, which will generate even more force. And just to explain the reason here, kind of the why behind this principle is that it's easier to depolarize a smaller neuron. So if I want to lift a piece of paper, right, literally a piece of paper less than a pound, I'm not going to waste time depolarizing really thick neurons. That's just not efficient for the body. I'm going to start off small. I'm going to start with those really tiny neurons that are attached to the smallest fibers in that muscle, and I'm going to recruit those first. And then I'm going to see if that's enough force to overcome the load that I'm trying to overcome. And then as needed, I'm going to recruit fibers that are slightly bigger in size before I get to the biggest fibers. I'm going to save that for last, because those fibers are attached to neurons that are harder to depolarize. It's going to take more energy to depolarize thicker neurons than it will to depolarize smaller neurons that are attached to a smaller number of fibers. So it's just more efficient for the body to start with small and then, as needed, recruit additional fibers for more force. All right. The last thing that we'll look at here is the velocity of shortening. This is really how the muscle contraction proceeds. So when the muscle contracts isotonically, and remember, isotonic means that the load is overcome, the tension levels off and stays the same, the load is eventually overcome and lifted. And so when a muscle contracts isotonically, the latent period of shortening is going to increase as the load increases. And if we think back to the latent period was the time that it takes for the machinery to get warmed up. This is the period where there's no force generation occurring yet because calcium hasn't made its way to troponin to get the cross-bridge cycles going. So basically, there's a period where it takes some time for those things to occur, for that event of excitation, contraction, coupling to occur, and for cross-bridge cycling to begin. And so that sort of makes sense. The heavier the load that I'm trying to lift, right? If I'm trying to lift a really heavy load, it's going to take even more time to get the machinery warmed up. So for a heavier load, the latent period will also increase. The second thing that happens is the duration of shortening decreases. And the duration of shortening is the period with which the contraction occurs. So this will also make sense. If I'm lifting a heavier load, the period with which I can sustain that contraction will decrease as the load gets heavier. If I'm lifting a water bottle, right, which I'm lifting here, I can sustain this contraction for maybe an hour, maybe two, because it's a fairly light load. So my muscle can stay in a contracted state to overcome this load for a longer period of time. If I'm lifting a really heavy box full of books, I probably won't be able to sustain that contraction for more than maybe 10 or 15 minutes, right? Because the duration of shortening, the period with which that contraction can be sustained, will decrease as the load gets heavier. If I'm lifting a heavy piece of furniture, I can't sustain that contraction for more than a couple seconds. So as that load gets heavier, the duration of shortening decreases. The third factor here is the velocity of shortening, which is the speed with which that contraction can happen. And the velocity will decrease as the load increases. So if I can lift this water bottle really quickly, that's the velocity. I can grab it right up, right, with a fast or high velocity. If the load was heavier, it would take me a longer time to lift that load. Okay, if it were a heavy box of books, it would take me a couple seconds, right, to actually, gradually lift that off the ground. And so that's the velocity. That's how fast the contraction can happen. So the rate of change of distance is shortened. And this is going to reach 0 when the load is at its maximum. And then it's going to be the greatest when there's no load. That is to say that I can lift an empty box much faster than I can lift a box full of books. So on our curve here, here's zero load. Notice how fast the velocity is, right? This is why when you're lifting something, let's say, again, a box, right? Let's say you're lifting a box and you thought there were books in it and you attempted to lift it, it would kind of just, grab right up off the ground. Whereas if it was full of books, that would take a much longer time. And when the load is at, the load is up here, so the load is at 0, the velocity is at the maximum. When the load is at its greatest, the velocity is at 0. That is to say that if there's a load that you cannot overcome, the velocity is 0 because there's no movement. All right. So when the load is 0, velocity is the highest. When the load is the highest, velocity is 0. All right. The last illustration here is just to show how the slope of the curve, which is the distance shortened against time, that gives us the slope, which is the velocity, or how fast that load is overcome. And if we compare that with a heavy load in red here, an intermediate load in purple, and then a 0 load in green. So a couple things to notice. One is notice that the latent period increases as the load gets heavier. So that latent period, the period where there's no force generation, gets longer and longer as the load is heavier. Notice the distance shortening decreases. So the distance that the load can be lifted, or the distance shortening rather, is also going to be decreased as the load gets heavier. And as the load goes to zero, the distance of shortening can get larger. The third thing is notice the slope, the velocity. Notice that for a zero load, the velocity is going to be higher. It's going to be a greater slope. And then for a heavier load, the velocity is going to decrease as that slope decreases. Okay, so just to compare how the latent period changes, the duration of contraction changes, and the velocity changes as the load goes from zero to a much heavier load. Okay. All right, let's look at these checkpoint questions in the time we have remaining. So take a look at these questions.